Hello everyone. This is the presentation conducted by Cheng Zhang for CVPR 2023. The title of our paper is TokenHPE, Learning Orientation Tokens for Efficient Head Pose Estimation via Transformers. First, we will give you a short 1-minute preview. In this paper, we identified 3 cues from head images, namely, neighborhood similarities, significant facial changes, and critical minority relationships. To leverage the observed findings, we propose a novel critical minority relationship-aware method based on the transformer. Besides, a token guide multi-loss function is designed to guide the orientation tokens learn the regional similarities and relationships. Experiments show that our method achieves better performance compared with state-of-the-art methods. Moreover, we provide visualizations to illustrate our method can learn the facial part relationships and orientation characteristics. From now on, we will provide more details of our work. The first is the introduction section. In some challenging scenarios, such as extreme head poses and serious occlusions, many remarkable facial parts are missing, which causes the head pose hard to predict. Therefore, in this work, we propose 3 findings of intrinsic facial part relationships to alleviate these obstacles and facilitate HPE. First, neighborhood similarities. Second, significant facial changes. Specifically, we observe that 2 facial regions can be distinguished by a significant facial part change. Third, critical minority relationships. We find that there still exist some important relationships that are helpful for prediction despite serious missing. For example, if a person's mouth is occluded, the head pose can be determined by the geometric spatial relationships of the eyes, nose, and the outline of the face. Based on these findings, we propose a novel critical minority relationship-aware method. Here is the mind map of our work. Then we introduce our methodology. In this paper, we introduce a novel token learning method for head pose estimation. Our model consists of 4 parts. First, visual token construction. In this part, an original input RGB image is transformed into visual tokens by a linear projection after being processed by a feature extractor. Then, a positional embedding is added to each visual token because spatial relationships are essential for head pose estimation. Second, orientation token construction. We divide the head pose panoramic overview into several basic regions according to the intrinsic facial part relationships. Generally, we follow the principle that head poses in the same region are similar, and the opposite head poses are symmetric. For instance, in Strategy 1, pitch direction, we set 30 degree as the division degree because of the appearance or disappearance of the nostril. In Strategy 2, we divide the yaw direction in a finer granularity because the significant facial part changes are complex when pitch angle is little. Given a set of basic orientation regions, we prepend the same number of learnable vectors, symbolized as DIR tokens, to represent these regions. Part 3. Transformer Module and MLP Head. We first introduce the transformer blocks. The input are the visual tokens and DIR tokens. The DIR tokens are selected as the output of transformer, whereas the visual tokens are not used in the following steps. The orientation tokens are transformed to rotation matrices for training and prediction. First, a linear projection is applied to each DIR token to obtain a 6D representation. Then the orientation matrix is obtained by the Gram-Schmidt process. A set of intermediate rotation matrices are generated by the transformation above. Then, they are concatenated and flattened as the input of the MLP head in order to obtain the final prediction rotation matrix. In the training stage, the intermediate and the final prediction rotation matrices are used for calculating the loss, while in the prediction stage, only the final rotation matrix is used for prediction. The last part. Token learning-based prediction. We designed a novel token guide multi-loss function for training the orientation tokens. The overall loss consists of 2 parts, namely, the orientation token loss and the prediction loss. A hyperparameter alpha is set to balance the 2 losses. Since the prediction of the proposed model is a rotation matrix, we measure the loss by the geodesic distance between 2 rotation matrices. Orientation token loss is the loss between the ground truth rotation matrix and the rotation matrix of the orientation token, which represents the same basic orientation region as the actual head pose. This is achieved by a special identity function that determines if a ground truth head pose lies in a specific basic region. The prediction loss is the loss between the ground truth rotation matrix and the final prediction rotation matrix. This is the summary of our methodology. Next, experimental results and visualization. We train and evaluate our model on 3 benchmark HPE datasets. We use 2 metrics to evaluate the models for comparison. Metric 1 is MAE, which is a standard metric. Because MAE is unreliable in extreme head poses, the MAEV results are also given for a more accurate measurement. In our experiments, we follow the train test protocols in FSA-Net. Results on the table show that our method is on par with state-of-the-art methods on the AFLW2000 dataset. The rest experiments show similar results. Compared to other methods that mainly based on CNN and its variants, our model is the only transformer-based token learning method, thus has a stronger ability to learn the facial relationships and the orientation characteristics in the basic regions. We provide visualizations to illustrate our method can learn the facial part relationships and orientation characteristics. First, the heat map of head pose predictions. Results show that our method can learn the crucial minority relationships of facial parts despite serious facial part missing. We calculate the cosine similarities of the learned orientation tokens. Results show that the neighbored tokens are highly similar and the tokens that represent symmetric facial regions have higher similarity scores than the tokens that represent other unrelated regions. Next, we visualize the attention interactions among orientation tokens in different transformer blocks in inference. We can observe that as the network deepens, each orientation token tends to rely on its neighbor region tokens and spatial symmetric tokens. More visualizations are provided in the supplementary material. At last, conclusion. In this work, we introduced 3 findings on head images. To leverage these properties, we utilized the transformer to learn the facial part relationships and designed several orientation tokens according to panoramic overview partitions. The success of TokenHPE demonstrates the importance of orientation cues in the head pose estimation task. We hope this initial work can shed light on further research on token learning methods for HPE. This is the last slide. Thank you for listening to our presentation.